Today I am here to discuss a topic from environmental engineering, that is sedimentation. Sedimentation is a very easy topic, and in GATE every year or every alternate year has been asked. It is a very easy topic. So I'll discuss this topic in detail. Sedimentation. Sedimentation is a treatment unit which is used in the raw water treatment plant for the removal of suspended solids. Like if the source of water is from a river, so a river will consist of heavy suspended impurities. It can be a big suspended impurities or a finer suspended impurities. Those which are larger in nature, that is whose size are bigger, are retained on a treatment unit known as screens, and the finer impurities are passed through the screens. So for those fine impurities, a treatment unit known as a sedimentation tank is used so that we can remove those finer impurities. So what we do is, in a sedimentation tank, this is a sedimentation tank, what we do is we allow the water to stand in this tank, or in other words we say that we remove the turbulence of water so that the particles which are present in suspension in water can easily settle down. These particles which are present along with the water in suspension can easily settle down. Right? Now, these particles settle due to their own self-weight. There is no other force acting on these particles. So when you remove the turbulence of water, what happens is these particles starts settling because of their self-weight. So the weight is one of the most important criteria when we talk about sedimentation. From this concept, I'll take the basic principle for sedimentation. What the basic principle for sedimentation tank, for sedimentation is nothing but specific gravity. The basic principle is nothing but specific gravity. Now, what is specific gravity? What do you mean by specific gravity? It is denoted by G, and it is defined as the weight of solids at a given volume divided by the weight of fluid. The weight of fluid. Weight of fluid in our case is nothing but water. So I will write it is the weight of solids at a given volume divided by weight of water at the same volume. At the same volume. That means the volume of solids and volume of water here is equal. That is, volume of solids is equals to volume of water. This is the basic principle for sedimentation. The weight of solid is responsible for removal of these suspended particles which are present along with the water. Now, these solids can be of two types. The suspended solids which are present can be of two types. One, it can be inorganic, other can be organic in nature. So, for inorganic particles, your specific gravity, the value of G, lies in the range of 2.6 to 2.9. 2.6 to 2.9, and is generally taken as 2.65. And for organic particles, G is in the range of 1 to 2, and it is generally taken as 1.2 in the case of organic solids. Right? So the basic principle is again specific gravity. Coming to the next part, the important part, what are the factors which governs the sedimentation process? What are the factors which governs the sedimentation process? Factors. The first factor The first factor is velocity of flow in the sedimentation tank. The velocity of flow. Velocity of flow, we call it as Vf. If the flow velocity is more, or I can say if the turbulence in this kind of tank is more, so what will happen? Your suspended particles will always remain in suspension. The turbulence of water will not allow the suspended solids to settle down. So what we do is we reduce the turbulence, or we totally remove the turbulence in case of sedimentation tank. So if your flow velocity is less, that means your efficiency for sedimentation will be more. Your efficiency for sedimentation will be more. The second factor is viscosity. Viscosity. If the viscosity of a fluid is more, let us take an example of, let us say, honey. If you dip something in honey, if you leave a particle in honey, what will happen? It will not just settle down. There will be a viscous force which will resist the motion of that dipping particles. So if your viscosity is high, it will resist the motion of your particle. So in this case, if the viscosity is less, and viscosity is dependent on temperature. If you increase the temperature, your viscosity reduces. So if you increase the temperature, if your temperature is more, then your viscosity will be less and your efficiency will be more. Your efficiency will be more. The third factor, the most important factor in case of sedimentation, is the size. Third factor is the size of particle. The size of particle. The size of particle. The settling velocity. What is settling velocity? I'll discuss that in detail. But for the time being, the settling velocity, the particle settles with a velocity, is known as settling velocity. So the settling velocity of a particle is directly proportional to the square of the diameter of the particle. That means larger the diameter, more will be the settling velocity. And more will be the settling velocity, faster will be the rate of your sedimentation. So your settling velocity Vs is directly proportional to d square. This is the most important part in case of sedimentation. We'll have a derivation, we'll have a link, I'll prove it that Vs is directly proportional to the square of the diameter. These were the factors which play an important role in the case of sedimentation. Now let us consider a sedimentation tank and a particle which is settling in the tank. If this particle is settling in the tank, it is settling due to its self-weight W, right? While this particle is settling, it will experience a buoyancy force from water. So there will be an upward force, we call it as FB, that is buoyant force, which is exerted by water on the particle. There will be another force. There will be one more force which will be due to the motion of this particle. Since this particle is moving down, there will be a drag force. There will be a drag force on this particle. So the drag force is always opposite to the motion of your particle. So there will be another force known as drag force. When you apply the equation, you will get an equation that is drag force plus buoyant force is equals to the weight. Drag force plus buoyant force is equals to weight. Now, if we know that force is equals to m into g. We know that force is equals to mass into gravity. We also know that density is equals to mass upon volume. Right? if I write mass is equals to rho into volume, mass is equals to rho into volume. If I substitute here, we get force is equals to rho into V into G. Rho into V into G. This term, rho into G. This rho into G is nothing but gamma. Yes, this rho into G is nothing but unit weight, gamma. So I can write force is equals to gamma into volume. Force is equals to gamma into volume. I will use this expression here. When I write buoyant force, your drag force, for drag force there is a direct formula. We write drag force as 1 by 2 CD rho A into Vs square. Here Vs is the settling velocity of this particle. Vs is the settling velocity of particle. A is the area of the particle. Rho is the density and CD is the drag coefficient and buoyant force. Buoyant force, I will write it in the form of gamma into volume. Now since buoyant force is exerted by water, so I will write the force as gamma W into V W is equals to the weight of the solid particle. Weight of the solid particle, again in terms of that relation gamma into volume, can be written as gamma of solids into volume of solids. Gamma of solids into volume of solids. Now, from the concept of specific gravity, we said that it was the unit weight of solid at a given volume to the weight of water at the same volume. So here I am talking about volume of solid is equals to volume of water. Volume of solids is equals to volume of water. So I can write VW is equals to Vs. I can write from the concept of specific gravity, VW is equals to Vs. I'm going to take this term to that side. The equation will become half CD rho A into Vs square is equals to, if I take this term to this side and replace this VW by Vs, it becomes, I can take Vs common, so it becomes gamma S minus gamma W into volume of solid. Please, I am using 2 V here. This is small v for Vs, settling velocity, and this is capital V for volume. So, we got this kind of expression. Let us substitute the values. Let us consider this particle has a diameter d. We can write area and volume of solids as, right, 1 by 2 into CD into rho into pi by 4 into d square into Vs square is equals to, from this term I am taking gamma W common. If I take gamma W common, it becomes gamma solid divided by gamma W. Gamma solid divided by gamma W is nothing but specific gravity G. So I can write, I am taking gamma W common, gamma W is equals to, this becomes G minus 1 into the volume of solid. The volume of solid, it is sphere, so volume of sphere is 4 by 3 pi into d by 2 whole cube. Pi into d by 2 whole cube. Now, we can cancel pi from pi. I can write this as 1 by 2 CD rho into d square divided by 4 into Vs square is equals to, this I can write it as rho into G into G minus 1 into 4 by 3 into d cube divided by 8. When I solve this equation, I can cancel some of the terms. I can cancel d square, I can cancel rho. When I solve, when I solve this expression for settling velocity, I'll get a value Vs is equals to under root of 4 by 3 g minus 1 into g d divided by cd. I'll get an expression 4 by 3 g minus 1 gd divided by cd. This is an expression for settling velocity. This is an expression for settling velocity. Now, I am considering a more specific case. I am considering a more specific case where I am considering my flow is in laminar state. I am considering that my flow is in laminar state. If I say that my flow is in laminar flow, that means your Reynolds number is less than 1. Your Reynolds number is less than 1, and the particle size which are settling have a diameter less than 0.1 mm. These are the two conditions when we say that the flow is laminar in our case. Reynolds number should be less than 1 and the diameter of particle should be less than 0.1 mm. Right? Now, so we know Reynolds number is given by rho into V, that is settling velocity, into d divided by rho Vd divided by mu. Mu is the dynamic viscosity of water. We also know in case of laminar flow, this CD, drag coefficient, CD is equals to 24 divided by Re. 24 divided by Re. If I substitute the value, I will get CD is equals to 24 divided by rho into Vs into d divided by mu. I will substitute the value of drag coefficient in this expression. I am going to substitute this value here. When I substitute this value, I'll get an expression Vs. When I substitute this here and I solve it, I'll get an expression for Vs as 1 divided by 18 mu into g minus 1 into rho g d square. 1 upon 18 mu g minus 1 rho g d square. This is the final expression for settling velocity. This is the final expression for settling velocity. In the case of sedimentation tank, we are going to use Vs. We are going to use Vs as the settling velocity for our particles. We are going to consider that it is a laminar state motion where the Reynolds number is less than 1 and diameter of particles which are settling have a size of less than 0.1 mm, and the velocity with which they are settling is given by 1 upon 18 mu g minus 1 rho g d square. It is very important from gate point of view. Questions have been asked on settling velocity and it is a very easy concept. So, we will remember Vs is equals to 1 upon 18 mu g minus 1 rho g d square. So, this is the expression for settling velocity. And I was talking when we were discussing the factors that the settling velocity is directly proportional to the square of the diameter of the particles. We have settling velocity Vs. It is directly proportional to the square of the diameter of the particle. Vs is directly proportional. Vs is directly proportional to the square of the diameter. That means larger will be the size of your particle, more will be the settling velocity. And if settling velocity is more, the rate of settlement will obviously be more. So this is the expression Vs is directly proportional to d square. Now we have derived a factor known as settling velocity. We have derived an expression for settling velocity. But what is settling velocity? What do you mean by settling velocity? Settling velocity is nothing. Let us take a concept, simple concept. What happens? Let us take a container. In this container, if you dip a particle, so what will happen? During the initial first few seconds, right after the dipping of the particle, this particle will accelerate. This particle will accelerate in the fluid or in water, and after some time the acceleration will become zero. Let us suppose at this point the acceleration became zero. At this point acceleration is equals to zero. If acceleration becomes zero, this particle starts moving with a constant velocity. When this particle starts to move with a constant velocity, that velocity is known as settling velocity. The particle starts moving with a constant velocity. That velocity is known as settling velocity. So settling velocity is nothing but, due to the self weight of a particle, initially it accelerates in water, and after some time the acceleration of the particle becomes zero, and thereafter that particle starts to settle with a constant velocity. That settling velocity is known as settling velocity. This is the concept for settling velocity. Now let us talk about sedimentation tanks. There are two types of sedimentation tank. There are two types. First is quiescent type or fixed type. Second one is continuous flow type. The difference between these two is, in the first case, water will not flow in the tank. Water will remain stagnant for a particular duration of time, and in the second case, there will be a continuous flow of water. Obviously, the velocity will be quite less, but there will be a continuous flow of water in the tank. But in case of quiescent type or fixed type, there will not be any continuous flow. Water will remain stagnant for a particular duration of time, and the settlement of particles is taken place. Let us discuss the first type. The first type is quiescent type. Quiescent type or fixed type. It is nothing but simple one tank there will be water at some depth. This is known as settling zone, and this is known as sludge zone. This is known as sludge zone. So what happens? There is no flow of water taking place here. There is no flow of water taking place. The turbulence is completely removed. The turbulence from this tank is completely removed, and the water is detained in this tank for a duration of 24 hours. 24 hours. The tank is designed in such a way that it has one settling zone and one sludge zone. Why? Because in the settling zone, the particles are going to settle, and in the sludge zone, the particles which are settled are collected here in this zone. After that, cleaning of this particular zone is done, so that this zone is provided so that your efficiency of the tank, your efficiency or the volume of the tank does not get reduced. So this additional area is provided for the settlement of sludge. Next, this kind of tank is designed for, this type of tank is designed for Q design is equals to 1.8 times of Q average. We know that the maximum daily demand is nothing but 1.8 times average daily demand. This type of tank is designed for 1.8 times of average daily demand, and the volume of this tank is calculated as Q design into detention time. Q design into detention time. So this is a fixed type or a quiescent type sedimentation tank. The second type is the important one, that is continuous flow type, which is important from our gate point of view, which is the continuous flow type. Continuous flow type. Now, for this kind of tank, we have some assumptions. For continuous flow types, there are some assumptions. The first assumption is we consider the removal of particle has taken place if it reaches the bottom of the tank. That is, if you're having a tank that is the continuous flow type, that means there will be constant inflow and outflow of water. There will be constant inflow and outflow of water. We assume that the removal of particle has taken place if it reaches the bottom of the settling tank. If your particle reaches this bottom, then we consider that removal has been taken place. Next assumption is that the particles are moving. The particles which are removed moves with a constant flow velocity. We are maintaining a continuous flow. We are applying a constant velocity. With the help of pump, we are providing a constant flow velocity. So we assume that the particles which are entering the tank are moving with this particular velocity. And also they are settling at some settling velocity. These are the assumptions. Now let us take a case. What is actually happening inside of sedimentation tank? We have two velocities. I said that we are assuming that the particles which are entering here are moving with a constant flow velocity, and these particles are also having some settling velocity, right? These particles have two velocities. One is in horizontal direction, other one is in vertical direction. So there will be a resultant velocity. There will be a direction of resultant velocity. Now I am saying this Vf is constant. Why? Because we are applying a pump, right? So this Vf is constant. Vs, is Vs changing? Is Vs changing? No, Vs is not changing because the size of the particle is not changing. We know that Vs is directly proportional to d square, and here the dimension or diameter of the particle is not changing. So both these velocities are constant. The flow velocity as well as the settling velocity, both are constant. And if both are constant, they will have a resultant as linear. They will have some resultant velocity in this direction. So the settlement is going to take place in this particular trajectory. It is having a horizontal velocity, it is having a vertical velocity. So the resultant velocity is coming out to be somewhat in this direction. Your removal is going to take place like this. And ultimately, here the particles are going to remove out. This is the length of the tank. This is the height of the tank. I have length of the tank. I have the height of the tank. I can write the detention time. Simple formula. Time. We know that time is equals to distance upon speed or displacement upon velocity. By this expression, by looking at this tank, we can write that in horizontal direction, the distance travelled by this particle is L. I am talking about limiting case, when the particle is present at the top and it is getting removed at this particular point. I am talking about a limiting case in which the particle is present at the top of the tank and it is getting removed at the cornermost point of the tank. So what is happening? If I calculate time in horizontal direction, the distance travelled by this particle is L. Distance travelled by is L. And in horizontal, what is the velocity here? In horizontal, the velocity is Vf. Vf. Now during this period, this motion, there is another motion taking place. That is the vertical movement, right? The particle is travelling a distance of 0 to L, and in the same time, it is also travelling a distance of this height, 0 to H. So it is travelling two distances, L and H. So I can write another value of detention time from height, that is height divided by the velocity in the vertical direction is nothing but settling velocity. So I can write Td is equals to L upon Vf is equals to H divided by Vs. A simple relation obtained for detention time. Length divided by flow velocity, height divided by settling velocity. The volume of the tank is computed as Qd into Td. Qd is nothing but design discharge, which is equal to 1.8 times of average daily demand. Next we can come to plan area. Plan area. We know that discharge Q is equals to area into velocity. The discharge is going to remain same. That is Qd divided by. For plan area, when we write this expression Q is equals to area into velocity, the velocity is always perpendicular to the area. If it is cross-section area, we will take the horizontal velocity, and if it is a plan area, we will take the perpendicular velocity, which is the settling velocity. So I am talking about plan area. To calculate plan area, it is discharge divided by settling velocity. Similarly, if we talk about cross-section area, it will be equal to Qd divided by the flow velocity. The sedimentation tank, it is designed for the removal of some particular solids, some value of D. Sedimentation tank is designed for the removal of some size of particle. Let us suppose D. I am saying that I will design my sedimentation tank for the removal of a minimum size particle. I will consider a size like, okay, let us suppose 0.3 mm is the size which I want to remove. So I will design in such a way that the minimum size of particles which are getting removed in my sedimentation tank is 0.3 mm. So I am saying the minimum size which is getting removed is D. Right? Corresponding to this D, this size, there will be a settling velocity. This settling velocity here is known as surface overflow rate. This velocity corresponding to this minimum size particle is nothing but surface overflow rate. Now, there will be cases where in your water, in your tank, in the sedimentation tank, there will be particles, let us suppose D1, which are greater than this particle size. There will be cases in your tank where this D1 size particles are greater than D. Yes, quite possible. There are various different sizes of particles which are present in water. So, we are removing this minimum size D. And the first case is my particle size is bigger than the concerned size, the minimum size. So in this case, what will happen? Since your D1 is greater than your design size of particle, so according to the relation, the settling velocity is directly proportional to the square of the diameter. Right? Square of the diameter. This D1 will have a settling velocity Vs1 and this D has a settling velocity Vs. Which among the two is greater? Since D1 is greater than D, according to the relation, Vs1 is greater than Vs. Now if I write the expression for detention time, TD1 is equals to nothing but H divided by Vs1, and here TD is equals to H divided by Vs2, or I will say Vs, simple Vs. Here Vs1 is greater than Vs. Since Vs1 is greater than Vs, that means your TD1 is less than TD. your TD1 is less than TD. If your TD1 is less than TD, that means what is the length? Length is equals to flow velocity into TD1, or length is equals to flow velocity into TD. Here TD is more. Your L1, in this case, L1 will be less than L. L1 is less than L. That means the particle size which are having a diameter greater than D are getting removed somewhere here. L1. They are not requiring the full length of the tank. They are not requiring the full length of the tank. So what I am trying to say is, if the diameter of particles are greater than your concerned size, then definitely they will be 100% removed in the sedimentation tank. They will be 100% removed in the sedimentation tank. There is another case in which the particle size is less than. Second case, this particle size D1 is less than D. Now if this particle size D1 is less than D, what will happen? If this particular size is less than D, that means your VS1 will be less than VS. If your VS1 is less than VS, that means your detention time TD1 will be more than TD. Your detention time will be more than TD, and if your detention time TD1 is more than your detention time, that means the length required by the particle to settle will be more than L. This is your L, and this particle whose size is less than your concerned size will require a length more than that of L. That is, this is L1. So in this case, the removal of this particle is not taking place. The removal of this particle is not taking place, as it is requiring a length larger than your length of your sedimentation tank. So in this case, there will be no removal of these particles. But there are cases. It depends on where the particles are present. Like, if this particle is present on the top, it is requiring a length greater than L. Let us suppose if this particle is present here, there is a possibility that it can get removed somewhere here. So I will say that if your concerned size of particle is less than your size, I will say that if the size of the particle are less than your concerned size of the particle, in that case, there will be partial removal of those particles. There will not be a complete removal, but there will be a partial removal for those kind of particles. How to calculate those particles which are settled, or I will say how much percentage of particles whose size are smaller than your concerned size are going to be removed. There is a method to calculate that. I'm going to discuss that just now. So what we do is, when the diameter is less than your concerned size diameter, so we calculate percentage of particles removed. It is given by the settling velocity corresponding to your D1 particle, Vs1, divided by the settling velocity of your concerned particles, or I can say the surface overflow rate, the concerned settling velocity concerned to your concerned particles, Vs, into 100. By this expression, you'll get how much percentage of that particle is going to get removed. How much percentage of that particles are going to get removed. Let us take an example. Let us take an example. Let us suppose we have different sizes. Let us suppose in mm we have different sizes and some quantity in grams. Let us say 1, 0.9, 0.8, 0.7, 0.6. Let us suppose some weight I am having 200, some 100 grams, then some 200 grams and some 300 grams and some 200 grams. So the total comes out to be 1000 gram. And I am saying that I am designing my treatment unit as per this particular size. That means my D, small d, is equals to 0.8. 0.8. I am assuming, no, not I am assuming, I am saying that the particles which are greater than the size of 0.8, that is 1 and 0.9, will get 100% removed, and the sizes, let us say, for 0.7 and 0.6, let us suppose this is 60% removed and these are 40% removed. These are 40% removed. Now, how to calculate the overall efficiency of your sedimentation tank? How to calculate, with these variation of sizes, how to calculate the overall efficiency of your sedimentation tank? It is simple. Your efficiency will be given by, let us see, for the first three sizes, what is the total quantity? 200 plus 100 plus 200, that is 500 grams. 500 grams is getting completely removed. From the tank. Plus, what is the next? 0.7. The size of 0.7, which are present in a total quantity of 300 grams, are 60% removed. And they are 60% removed. So, 300 into 60 divided by 100. Plus, that is, next is the size of 0.6, which are present in a total quantity of 200 grams. 200 grams are getting removed 40% only. So, 200 into 40 divided by 100. 200 into 40 divided by 100 divided by the total quantity. The total quantity is 1000 grams into 100. This expression will give you the total efficiency. There will be some value. It will give you the total efficiency in percentage. Right. This is one method. The other method will be, he will give you some settling velocities corresponding to each particle size. He can give you some settling velocities. Like, for example, for D, Vs, D1, Vs, I will write it like this as D1, Vs1, D2, Vs2, D, Vs, D3, Vs3 and D4, Vs4. Now he says that D1 and D2 are greater than D and D3 and D4 are less than D. For this case, we have no problem as all these will be 100% removed as the diameter is greater than the concerned diameter. But in this case, what happens? There will be some partial removal. How to calculate that partial removal when settling velocities are given? Now he is saying that your tank is designed for this case. D with the settling velocity of Vs. Now I want to calculate how much percentage of this size of particle is getting removed. So for that, I am going to use the percentage removal. The percentage removal is equals to the settling velocity of these particles, that is Vs3, divided by the settling velocity for the designed particle, that is Vs. Settling velocity of this particle divided by the settling velocity of this concerned particles into 100. From this expression, I will get my percentage removal. Similarly for this, the percentage removal will be the settling velocity Vs4 divided by Vs into 100. From both these cases, we'll get the percentage removal of particles of this size. Particle removal of this size. For the final expression, the efficiency, the final efficiency will be given by as summation of percentage of quantity into percentage removal divided by percentage quantity into percentage removal divided by the total quantity into 100. This expression will give you the entire or the overall efficiency for your sedimentation tank. Directly you can apply the formula and get the efficiency for the sedimentation tank. Coming to the design data. The first is the plan area. We have already discussed the plan area is given as B into L, the breadth into length. The breadth into length will give you the plan area, which is equals to QD divided by Vs. QD divided by Vs, or I will write surface overflow rate. This surface overflow rate can be in liters per meter square per day or meter cubes per meter square per day. If you see the units for surface overflow rate, it is meter cubes per meter square per day. It is nothing but the units of velocity. Surface overflow rate is nothing but the settling velocity of your design concerned size of particle. So this is the units. The detention time. This is plan area. Second is detention time. The detention time for PST, plain sedimentation tank, is taken as 4 to 8 hours for PST and 2 to 4 hours for coagulation aided sedimentation. Coagulation aided sedimentation. Volume is calculated as QD into detention time. The flow velocity is taken in the range of 0.15 to 0.9 meters per minute. 0.15 to 0.9 meters per minute, and it is generally taken as 0.3 meters per minute. 0.3 meters per minute. Next, length is calculated as velocity of flow into detention time. Velocity of flow into detention time. The next design parameter is width to depth ratio or length to width ratio. L divided by W is equals to 4:1. The length to width ratio is given as 4:1. And last, sludge zone. Sludge zone is provided as 0.8 to 1.2 meters. 0.8 to 1.2 meters. These are some design values, design data for sedimentation tank. Let us take a simple question which was asked in GATE 2017. The question says, a municipal corporation is required to treat 1000 meter cubes per day of water, and it was found that the SOR is giving Q as 1000 meter cubes per day. This was asked in GATE 2017. He has given Q is equal to 1000 meter cubes per day of water, and it says it is found that the surface overflow rate of 20 meters per day will produce a satisfactory removal of discrete suspended particle at a depth of 3 meters. So he has given us surface overflow rate as 20 meters per day. And he is saying some depth he has given as 3 meters. He is asking the diameter of the circular tank. We need to find the diameter of the tank. Diameter of the tank. Simple question. What he has given? He has given discharge. He has given surface overflow rate. We know that area, plan area is equals to Q design, that is 1000, or I will write QD divided by surface overflow rate. QD divided by surface overflow rate. QD is given as 1000 meter cubes per day, and the SOR is given as 20 meters per day. 20 meters per day. So you can directly say the area is coming out to be 50 meter square. The area is 50 meters square, and he's saying that the diameter of circular settling tank, that means your area is nothing but pi by 4 into d square is equals to 50 meters square. When you calculate, you will get a value d is equals to 7.97 meters. So diameter is approximately equal to 8 meters. Simple question asked in GATE 2017. The concept for sedimentation tanks are very easy. Just he'll give all the data. You need to just apply the formulas and get the answers.